Now I want to briefly talk about the process of generating X-rays. It's very schematic what I will introduce here. I'm mainly keen on discussing two major effects that we have, two major experimental parameters that are under the control of the experimenter. And so we are having here a negatively charged cathode, that's the source of the electrons. We have a filament here, and we use an electrical current that runs through the filament here in green that is heating up the cathode. So why is this necessary? Why do we need a current here? Well, think about it. What we want to do is we want to produce X-rays, and the X-rays, the production is being done, as we will see shortly, by the release of electrons from the cathode. If we heat up the cathode, we increase the kinetic energy of the electrons, and therefore the probability that an electron is being released. Then what happens between the cathode and anode? The electrons are accelerated by the electric field. The energy of the electron is equal to its charge times the voltage difference between cathode and anode. So that gives us the electron volts. Here is the charge. This is a fairly high charge, negative here, positive here. So the electrons are being emitted from the cathode and attracted towards the anode. So in the anode we have a target, and this is a metal target. Typically it's tungsten. We'll discuss in a short while why. So they hit the anode, and then it's the voltage between cathode and anode is up to 150 kilovolts. So these electrons, as they interact with the target here, the metal target, they will produce X-rays. And these X-rays are then emitted and used for imaging. Now in this animation that you see here, let us not be fooled. The X-rays that are produced in the anode target, they go in all sorts of direction, but we have metal shielding of the X-ray tube here. We are just leaving a window open here, so it's only through that window that the X-rays can penetrate and produce a beam of X-rays in the direction. Typically, the intensity of the beam is expressed as power per area. It is proportional, the beam is proportional to the number of X-rays. The number of X-rays is proportional to the number of electrons that hit the target, and the number of electrons that hit the target, the anode here, is proportional to the current in the cathode, so the filament current. The energy of the X-rays is somehow related to the voltage difference between anode and cathode, here and here. If we have 150 kilovolts, then we produce electrons with an energy that they hit the target of 150 kiloelectron volts. If we use only 50 kilovolts, then the energy of the electrons as they hit the tungsten target is 50 kiloelectron volts. So these are the two things that we can control. We can control the filament current, and so increase the tube current. That is, we can increase the number of photons, the number of electrons, and therefore the number of photons per second that are being emitted. And with the voltage between the cathode and the anode, we control the maximal energy of the photons that are being emitted. That is, we control the energy of the electrons when they hit the target. Here is just a scheme here showing the same thing again. We have the filament current, we have the anode target, the voltage between here, and the whole thing is in a tube in the vacuum. Otherwise the electrons will never see their target. Now, ideally, I said the electrons have an energy of 150 kiloelectron volts, and ideally this will produce X-rays of energy for each photon, for each electron that hits the target of 150 kiloelectron volts. That would be the ideal case, but this is not the reality, and we're going to have to look at the emission of X-rays generated in an X-ray tube, and we're going to look at the interaction of the electron with a stationary atom. We'll look at this as a collision. So we have the nucleus here. We have the electron as it comes in. It is attracted by Coulomb force, so it changes direction. Now when it changes direction, we can look at this as a collision. We have at the beginning, we have the atom stationary. We have the electron with a certain linear momentum. It leaves after it has passed by the nucleus with another momentum, but now as it has been deflected, the momentum has changed. And conservation of linear momentum, as this is a collision, requires that there is another object with a linear momentum that is involved in this collision, and that's the emission of a photon. So we have conservation of linear momentum. The initial linear momentum of the electron is equal to the final momentum of the electron plus the momentum of the photon. Now, if we look at Coulomb, and we're just going to talk here, Coulomb basically says, the Coulomb force says that the electron is subjected to an acceleration which is proportional to the charge of the electron, QE, proportional to the atomic number, Z, the number of protons in the nucleus, divided by the mass of the electron and the distance to the nucleus. So the acceleration of the electron, that is a change in linear momentum, cannot a priori ab initio be defined. We won't be getting 150 kiloelectron volts. It depends on where the electron is deflected with a nucleus, how close this interaction is, by how much is it deflected, etc. So we do not a priori know this distance r, so we will not get a fixed acceleration, and so we will not get a fixed photon energy. We'll get a mix of photon energy. Or the way you can imagine this is the electron comes to the target, the anode target, is deflected, releases a photon. Then a few micrometers later, or a few atoms later, it interacts with the next nucleus and it's deflected again, and it releases again a photon, and so on and so on. So there's a subsequent release of the photon until that electron essentially comes to rest. But it's not a single photon in general that's being released. So we have from these laws, we have neither information on the directionality of the radiation, nor on the photon energy that is being released. So, but we do know a maximum value for the energy of the photon that's being released. How is this defined? Well, the definition here is this. We have the electron comes in with a kinetic energy of 150 kiloelectron volt, and let's assume it is, by whatever process in the tissue, in the anode target, it is immediately stopped. Then the energy of the electron is converted into the energy of a photon, and that is then equals to the kinetic energy of the electron. If you have 150 kilovolts at the anode cathode, the energy of the electron is 150 kiloelectron volt. By conservation of energy, the maximum photon energy is 150 kiloelectron volt. So this effect of that the electron is subsequently decelerated, it loses its kinetic energy. This is a braking effect on the electron, and the term for this that is being used is Bremsstrahlung. It's a German term which basically means braking radiation. Why is it German? Well, this is historical. Until 1945, Germany was if not the leading country in physics. So that's where we are with German terms. So if we now look here at the relative intensity of this Bremsstrahlung as a function of wavelength, then we have decreasing energy to the right, so the highest energy is on the left. And we can see here the maximum energy for a voltage of 50 kilovolts is 50 kiloelectron volts. This is the maximum energy that we have here. As we decrease the voltage to 40 kilovolts, the maximum energy is reduced. We cannot go higher than that maximum energy here of 40 kiloelectron volts. We go to 30 kilovolts. We are now here, and finally 20 kilovolts. So we have this spectrum of photon energy for a given wavelength, that is a given energy, and this is what is called the Bremsstrahlung continuum. Now we have elastic scattering. I don't want to talk too much about it. We have the probability is proportional to Z, the atomic number squared, divided by the energy of the electron squared. And then we have inelastic scattering. There the probability is proportional to Z squared. Inelastic scattering meaning that we have the electron which is releasing a photon. So what does this mean if it is proportional to Z squared? It means to generate as much per electron, as many photons per electron, we want to use a material with high Z. And this is the explanation here is why tungsten is a good target. It has a high atomic number, a high number of protons in the nucleus. So far we've talked about the Bremsstrahlung continuum. We've explained why this breaking of the electrons in the tissue is not deterministic in defining a precise X-ray energy. And there is another effect that I need to discuss here that characterize the X-ray spectrum, and this is the question of what are characteristic, that is fluorescent X-rays. The mechanism that we are looking at is we have the electron that interacts with the atom, and here the interaction is reminiscent of playing billiard. Think of the electron that comes in as like a billiard ball. It hits another electron like another billiard ball. That inner shell electron is then bumped out of its shell and leaves the atom. What does this mean now? That the atom is excited, is in a higher energy state. It no longer has, say, in the K shell, its electron, so it's a higher energy state. In other words, we have a vacancy in the K shell, for example. So to recap, the electron comes in, bumps a K shell electron out of the K shell, creates a vacancy, so there is a spot to be filled. And here's the process that happens, that this inner shell electron, this vacancy here at this point, is being replenished by an outer shell electron. This can be cascading, so it can be not just one, but here's the case of one. We have created this vacancy by a collision. The electron is missing. The atom has a higher energy state, so it wants to go back to its ground state. So an outer shell electron here from the M shell falls down into the K shell here, and as it does so, it will release a photon whose energy is exactly the difference in binding energy. Here we have 2.5 kiloelectron volts of binding energy in the M shell. We have 69.7 kiloelectron volts in the K shell. The difference in energy is given off as a single photon. That's the characteristic X-ray, and this will have, as you can do the math here, is exactly 67 kiloelectron volt K shell X-ray. Now looking here, this is graphically illustrated here. We have the electron that impacts the K shell electron, so it plays billiard. The two electrons leave the atom, and then you see that the outer shell electron falls into the K shell, and as it does so, it releases the characteristic X-ray with a very defined frequency. So as a consequence, if we look at the relative intensity of emitted X-rays from a target, here it's a molybdenum target, bombarded with electrons with energy exposed to 35 kilovolts. We have the Bremsstrahlung continuum, we've discussed on the preceding slide, and then we have these characteristic X-rays, these spikes here. As pointed out here, the energy difference between the energy levels is very precise, so this will produce a very precise photon, and these are those characteristic or fluorescent X-rays that are added to the spectrum, that is, to the X-rays that are being produced. Now there's one effect that I'd like to discuss, just mention here. This is Auger emission. So if you have the excited atom here on the beginning, we have the vacancy, we have the excited atom. Now instead of producing a cascading electron falling down, when the electron falls down into the inner shell, of producing a photon, instead of producing a photon, this can also result in a emitted electron. So the energy, instead of being transferred here to a photon, it is here transferred to an outer shell electron, and this produces an Auger electron. So we have seen here, this is a 67 kiloelectron volt energy difference, which produces 67 kiloelectron volt characteristic X-ray, and here we're having an Auger electron from the M shell at 64.5 kiloelectron volt. It is reduced because we have to take into account that the binding energy has to be overcome, so it will have a kinetic energy of 64.5 kiloelectron volt. This is Auger emission, and that electron, of course, will then diffuse and interact with the tungsten target as if it were an electron coming from the outside at 64.5 kiloelectron volt. So here's the process in this animation, the Auger process. Illustrated, we have the initial state, we have the incident electron that produces the vacancy here in the K shell. As the electron falls into the K shell, an L shell electron here is emitted as a Auger electron. Now this concludes the introduction to the generation of X-rays. In the next week we will discuss the interaction of X-rays with tissue. The principal modes will be discussed. We'll introduce some important relationships and as well include a small primer on X-ray safety considerations and protection procedures.